So now we understand how processor addresses I/O devices either using memory mapped I/O or isolated I/O. A very related question is how does the CPU know if a device is ready to do data transfer? And this is important because most of the I/O devices are very slow compared to the CPU. So there are two approaches for doing this, polling and interrupt. In polling, CPU continuously monitors the I/O device to check if it is ready. However, the downside of this approach is that CPU might spend billions of cycles before the device actually becomes ready. On the upside, as soon as the device becomes ready, CPU reacts fast for the data transfer. In the second approach, instead of CPU monitoring the device, it's the device that lets the CPU know when it becomes ready. And the mechanism that it uses is that it sends a signal to the CPU called an interrupt signal. The downside of this approach is that the response of CPU is a little bit slow, and this is because when the interrupt arrives, CPU is already doing something else, so it needs to stop doing that, save the state, and then responds to the interrupt. However, on the upside, the CPU utilization is much better. CPU is not wasting now billions of cycles just to check if the device is ready. It's doing something useful in those cycles. So let's see how this interrupt interface really works. So when the device is ready, IO controller sends an interrupt request to the CPU. CPU stops doing what it has been doing, saves the state and acknowledges the interrupt, and then the data transfer really takes place. So let's see what happens on an interrupt. So CPU saves the address of the current instruction that it's executing. And this is because after handling the interrupt, CPU needs to come back to this place and continue execution from here. Then it jumps to the interrupt handler that tells the CPU how to handle communication with this device. Then handle the interrupt. That means really doing the IO operation. And during this phase, we might need to preserve some registers. This is very much similar to what we did in a procedure call. There were some callee saved register and some caller saved registers. So the same thing applies here as well. Then once the IO transfer is complete, the processor needs to start executing the program where it stopped. So it reads this PC which was saved in the first place, reloads it in the PC register and start execution from there. And there is a special instruction to return from an interrupt handler. If you remember, we used a regular move instruction to return from a function call. However, to return from an interrupt handler, there is a special instruction. Now, most of this functionality is very similar to a function call. CPU needs to save the PC, then jump to the interrupt handler, really execute the handler or do the IO operation with the device, and then come back and start executing from the place where it stopped. Okay, so what happens if there are more than one device that we want to connect to the CPU? Well, one situation can be this. You just connect one device to one of the ports to the CPU. However, CPU need to have at least as many ports as the number of devices. But what if there are more devices we want to connect than there are number of ports on the CPU? We can do something like this. We can combine multiple devices and connect them to one port at the CPU through an OR gate. However, what the CPU needs to do in this case is, since many devices are connected to one port, if there is an interrupt signal here, it needs to poll each of the devices to know which one is ready for the data transfer or which one raised the interrupt at that particular point. An alternate is to use an interrupt controller. Interrupt controller is a device that arbitrates among the connected devices to provide them access to the CPU services. Okay, so when we have many devices, we need to answer the following two questions. How does the CPU know where is an interrupt handler for a particular device? And if there are more than one device is raising the interrupt signal at the same time, which one should the CPU process first? So let's first talk about finding the interrupt handler. There are two approaches for this. In the first approach, whenever an interrupt arrives, CPU always jumps to a predefined address. and then it uses the ID of the device which interrupted to jump to the handler of that particular device. In the second case, CPU directly jumps to the handler of the device, and this approach is more commonly used and it's called vectored interrupts. So this is an interrupt vector table for ARM architecture. It tells us for which particular interrupt where is the memory location to which the CPU should jump to. So now let's talk about the second question, which interrupt should be handled first? Well, if there are many devices that want CPU services, CPU needs to prioritize them. So that's exactly what is done here. We prioritize the interrupts. So all the interrupts are assigned priorities, and a high priority interrupt is always handled before a low priority interrupt. Now, when a CPU is handling an interrupt, other interrupts can also come. So what happens in that case? Now, if CPU is handling an interrupt and a high priority interrupt arrives, CPU will stop executing the current interrupt and start executing the higher priority interrupt. Then once the higher priority interrupt finishes, it will take back the low priority interrupt from the place where it left. The second case is when CPU is executing a higher priority interrupt and a lower priority interrupt comes. In this case, CPU will just ignore the low priority interrupt for a while and keep executing the higher priority interrupt. So to know which one is the higher priority interrupt, CPU needs a priority register which tells what is the priority of the interrupt which is currently being handled. CPU can also mask some interrupts. That means if an interrupt arrives, CPU will not be informed that a device wants its services because CPU is probably doing something more important. And then there are also some interrupts that cannot be masked. These are for accessing some important services from the CPU, or these are for requesting some important services from the CPU. So this is how the priorities in ARM instruction set architectures look like. So these three are the highest priority interrupts. Reset is the highest, then non-maskable interrupt, and then hard fault. And for rest of the interrupts, the priorities can be decided by the user, can be decided by the programmer. So let's summarize the interrupt handling in CPUs. So the first thing that happens is a device becomes ready and it raises the interrupt signal. Then the signal is sent to the CPU. CPU monitors every cycle whether some devices needs its services or not. When it sees yes, there is a device which is ready, then it acknowledges the interrupt with the highest priority if there are more than one that are ready. So an acknowledgement signal gets sent to the device. Then the device, upon receiving the acknowledgement, sends the interrupt vector number that the CPU should jump to for servicing this device. Then upon receiving this number, CPU saves the state, for example, PC, registers, and so on, and jumps to the interrupt handler itself. Then it executes the code for doing the IO operation, and depending upon the device, CPU might need to save additional state than what it saved in the previous step. And then once the IO transfer is done, the CPU needs to restore the state and the program counter and return to the execution where it was interrupted when the device raised the interrupt signal.